Welcome to the Deep Dive. Today, we're plunging into a subject that feels incredibly relevant to our time. A fascinating paradox, really, sitting right at the intersection of technology and economics.
We're talking about this apparent contradiction, aren't we, between the, breathtaking speed of advancements we're seeing in artificial intelligence.
And then, on the other hand, this observed slowdown in productivity growth across many developed economies. It doesn't quite seem to add up.
It really is a clash of expectations, and the hard data. On one side, you have these AI systems getting rapidly better, matching or even exceeding human capabilities in more and more areas.
And this is fueled by just tremendous leaps in the underlying technology, driving soaring valuations for tech companies. You see it constantly.
That's right. You see it everywhere, from those viral AI demos generating complex images or text, all the way to AI tackling really hard problems like in drug discovery or material science.
Yeah, the sources we looked at point to a pretty fundamental shift in machine learning itself. It's moved beyond trying to sort of codify rigid human knowledge
Towards algorithms that learn these incredibly powerful patterns directly from massive data sets. And that shift has led to some truly dramatic improvement.
especially in areas like perception, understanding images or speech, and even some cognitive tasks.
Absolutely. If you look at something specific like image recognition error rates on the ImageNet dataset, they just plummeted.
Right, I saw those figures from
Right.
over 30% just a little over a decade ago, back in 2010.
Down to less than 5% by 2016. That's a huge improvement. And you see the big tech players, Google, Microsoft, Apple, Amazon, they're all investing heavily, positioning themselves as AI-first companies.
The sheer volume of activity is clear, too. The number of venture-backed AI startups more than quadrupled in the decade leading up to 2017, according to the sources. The technological progress just feels undeniable.
So you've got this clear evidence, technological acceleration, massive investment, but then you look at the aggregated data, specifically labor productivity growth.
And you see this widespread deceleration. It's quite stark in the United States, for example. Annual labor productivity growth averaged just 1.3% from 2005 to 2016.
And that figure is striking because it's less than half the rate we saw in the decade before that, from 1995 to 2004, when it was running at about 2.8%.
And this isn't just a U.S. story, is it? The sources show a very similar picture across the developed world.
That's correct. 28 out of 29 other OECD countries experience comparable slowdowns. The unweighted average growth rate for those countries fell from 2.3% annually between 95 and 04, down to just 1.1% from 2005 to 2015. It's a widespread phenomenon.
And the puzzle sort of deepens when you bring in broader economic measures. Real median income in the U.S., for instance, has largely stagnated since the late 1990s.
And some non-economic indicators of well-being, things like life expectancy, have even reversed course for certain demographic groups, which adds another layer of concern.
So our mission for this deep dive is to take the source material you've provided and really try to unpack this paradox. We want to understand the potential explanations being put forward.
And explore what the historical context might tell us, and what the future possibilities could be regarding this tension between rapid AI progress and, sluggish measured productivity.
Okay, so when trying to explain this paradox, this disconnect between all the buzz around AI and the actual aggregate statistics, the sources seem to focus on four main potential explanations.
That's right. They consider whether it might just be, false hopes, or maybe a matter of mismeasurement, or perhaps it's about redistribution of the gains, or even significant implementation lags.
Let's take that first one, false hopes.
Yeah.
The idea that maybe all the optimism about AI is simply overblown.
The research we looked at seems to largely dismiss that as the primary driver. The evidence of AI's increasing capabilities is just too compelling, too widespread to ignore.
Okay, so if it's not likely false hopes, that leaves us with the other three possibilities. Let's start with mismeasurement.
The argument here is that the benefits of many modern technologies, AI included, are simply not being fully captured by our traditional economic statistics like GDP and productivity measures.
And that makes a certain kind of intuitive sense in today's digital economy, doesn't it? So many digital goods and services might cost very little, maybe even be free.
Yet they provide enormous value to consumers. People spend vast amounts of time using them, but that value isn't easily captured in simple monetary terms in GDP.
Plus, you have complicating factors like global operations and things like offshore profit shifting that can muddy the measurement waters, too.
That's a fair point, and there's definitely some mismeasurement happening. Several studies have tried to quantify this using different methods, and they suggest that while it's a factor, it's probably not the entire explanation.
So mismeasurement alone doesn't seem big enough to account for the whole productivity slowdown we're seeing.
Likely not the substantial part, partly because measuring the benefits of new technologies has always been a challenge, you know? Think about the quality improvements from innovations in the past. They were hard to measure, too.
But there's a particularly interesting angle on mismeasurement that seems specific to AI, related to intangible capital.
Absolutely. This is quite important. AI is often used as a tool to build other forms of capital, particularly new software, but also things like improvements in human capital through training or organizational capital through redesigning business processes.
And these forms of capital are often intangible, hard to measure directly.
Exactly. So when businesses rapidly invest in this kind of unmeasured, intangible AI-related capital, standard growth accounting methods can struggle.
How so? What's the effect?
Well, think about it. If the investment, especially the labor input needed to build this intangible capital, happens now, but the output or the productivity gain only shows up later.
It can actually look like measured productivity is slowing down in the short run, even though you're investing for future gains.
Precisely. It creates a kind of J-curve effect in the statistics. The initial investment phase might actually look like a drag on measured productivity before the benefits materialize and push it upward later on.
Can you give an example of that?
Sure. Think about the labor inputs going into developing complex AI systems or redesigning entire workflows around them. One source points to a Brookings estimate
Yeah.
that around $80 billion was invested in autonomous vehicles between 2014 and 2017. Now, so far, there's been very little measured output gain from these vehicles operating widely in the economy.
Right, they're still mostly in development and testing phases.
Exactly. So if that $80 billion primarily represented labor spending on R&D and development, creating intangible capital, it could have actually lowered measured labor productivity by about 0.1% per year over those 3 years.
Because all that input, that labor cost, wasn't yet showing up as final measurable output in the GDP figures.
That's the potential dynamics. A mismeasurement, especially around this intangible AI capital formation, is certainly one piece of the puzzle.
Okay, so that's mismeasurement. What's the next potential explanation the sources discuss?
That would be the redistribution hypothesis. This idea suggests that the economic gains from new technologies, including AI, aren't being widely shared or broadly boosting the overall economy.
Instead, the argument is that they're becoming highly concentrated in a very small part of the economy.
Yes. Think about areas like online advertising or automated high-frequency financial trading. These activities can have significant zero-sum aspects, where gains for one player often correspond to losses for another, rather than growing the overall pie.
And this concentration can lead to what the sources call dissipative efforts. Can you explain that?
It means people and companies might end up spending resources not on creating new value, but essentially on fighting over or trying to capture those narrow, concentrated gains that already exist.
Like what kind of activities?
Things like intense lobbying to gain favorable regulations, or maybe excessive marketing efforts aimed purely at stealing market share rather than expanding the market, or even complex legal battles over intellectual property. These could all be seen as dissipative.
So resources are diverted from productive uses to rent-seeking or fighting over slices of the pie.
That's the concern. The evidence we see of growing income inequality and stagnant median income certainly aligns with the idea that gains are concentrated.
But do the sources conclude this is the main driver of the aggregate productivity slowdown?
There's still debate about the scale of the aggregate effect. While concentration is happening, it's less clear how much these dissipative activities are dragging down overall measured productivity growth across the entire economy. It's likely a contributing factor, but maybe not the whole story either.
Okay, so if mismeasurement and redistribution aren't the complete answer, that brings us to the explanation the sources seem to find most compelling: implementation lags.
Yes, this idea seems to have a lot of explanatory power, especially when you consider the nature of AI. It's built on the concept of AI as a general-purpose technology, or GPT.
Like electricity was, or maybe early computers and the internet. Technologies that are so fundamental they have the potential to impact almost every sector of the economy.
Exactly. But the key thing about GPTs is that they don't just plug and play instantly and boost productivity across the board.
Right, realizing the full productivity potential takes time because it requires waves of complementary innovations. Is that the idea?
That's precisely it. You need significant investment, not just in the core technology itself, the AI algorithms, the computing power, but also in developing new organizational structures.
New skills for the workforce, new business processes, and often new physical and intangible capital that actually works with a GPT.
And this whole process takes considerable time and investment. One source highlights that it took more than 25 years after the invention of the integrated circuit for the aggregate computer capital stock to really reach its plateau, its steady state in the economy.
There's a classic historical example often cited here, isn't there? The electrification of factories.
Yes, that's a perfect illustration. Even when electric motors became widely available in the late 19th century, factory productivity didn't suddenly soar overnight.
Why was that? What was the holdup?
Because the factories themselves were still designed around the old power source, typically a single large steam engine driving everything through this complex, inefficient system of belts and pulleys overhead.
So just swapping the steam engine for a big electric motor didn't fundamentally change things much initially.
Not nearly as much as you might think. It took about 30 years, roughly from the 1890s into the 1920s, for manufacturers to figure out and widely adopt the truly revolutionary complementary innovation,
Which was?
reorganizing the entire factory layout to use individual electric motors on each machine. This allowed for much more flexible workflows, better factory design, but it was a massive change.
And presumably there was resistance to that kind of radical change.
Indeed. It was partly held back by incumbent resistance, what some call the curse of knowledge,
Huh.
where the existing ways of doing things make it really hard to even see, let alone adopt, radically new and better methods.
And the sources emphasize just how significant the cost and effort involved in developing these complements can be, right? It's not trivial.
Far from it. Firms often end up spending several times more on things like business process redesign, training their employees on new systems, and developing entirely new workflows than they actually spend on the hardware and software of the GPT itself.
So the investment in the surrounding changes dwarfs the investment in the core tech.
Often, yes. And research bears this out. Studies have shown strong complementarities between, say, IT investments, investments in human capital development training, and organizational changes. Firms that manage to combine all three tend to see disproportionately higher market values and bigger productivity gains.
And interestingly, just like we discussed with the J-curve idea around mismeasurement of intangible capital.
The very process of implementing a GPT can actually reduce measured productivity initially. You have adjustment costs, employees spending time learning new systems instead of producing output, or maybe early stage activities requiring more labor before full automation kicks in.
Like those early autonomous vehicle projects, again, lots of human engineers, testers, safety drivers involved before they potentially displace human drivers at scale.
Exactly. So the implementation lag hypothesis suggests that the big productivity boost from AI is likely still coming, but it's simply taking time, maybe decades, to develop and deploy all the necessary complementary innovations across the entire economy.
Okay, that makes sense. Looking at historical patterns, are there any parallels to our current situation with AI that might offer some insight into whether this lag idea holds water?
There's a really striking analysis presented in the sources that does exactly that. It compares U.S. labor productivity growth after 1970, which marks the beginning of the IT or computer era.
With the periods from 1890 to 1940, which encompasses the rollout of portable electric power, the GPT we just discussed.
And when you put those two periods side by side, the patterns look remarkably similar.
How so? What are the similarities?
Well, both periods seem to have begun with roughly a quarter century of relatively slow productivity growth right after the invention of the core technology.
Okay, an initial sluggish phase.
Then both eras saw a distinct decade-long acceleration in productivity growth. For the IT era, that was roughly 1995 to 2004. For the electric power era, it was about 1915 to 1924.
So a boom followed the initial lag, and then what happened?
Interestingly, the slowdown in productivity growth that we've experienced since 2004 actually mirrors a similar slowdown that occurred from 1924 to 1932 in the electric power era.
That parallel is quite striking. What conclusion did the sources draw from this historical comparison, particularly regarding forecasting?
It leads to a really important, maybe even counterintuitive point about predicting the future. The analysis strongly suggests that past productivity growth rates are actually very poor predictors of future growth, especially when you're looking out over a decade or longer.
Really? So you can't just extrapolate from recent trends?
Apparently not reliably. The sources mention statistical regressions where the previous decade's productivity growth explains almost none of the variation in the next decade's growth. The R-squared values, which measure that explanatory power, are incredibly low, like 0.009 for labor productivity, almost zero predictive power.
So the fact that productivity growth has been slow recently, even though it echoes a past slowdown after a GPT rollout, doesn't necessarily mean we should be pessimistic about the future impact of AI.
According to this analysis, no. Historical stagnation, or even recent stagnation, doesn't automatically justify forward-looking pessimism, particularly when you're dealing with a technology that has the fundamental characteristics of a GPT, like AI seems to. Its potential might just not be showing up in the aggregate statistics yet.
Speaking of that potential, what does it actually look like in terms of the tasks AI could perform and the potential economic impact beyond just the current applications we already see?
Well, the technical capability seems vast. Some estimates suggest that around 45% of current U.S. work activities across pretty much all sectors could theoretically be automated using technologies that already exist today.
45%. That's a huge number. But you said theoretically.
Yes, and that's a crucial caveat. Technical feasibility is only one part of the equation. Economic factors like the cost of implementing the automation versus the cost of labor, regulatory hurdles, and social acceptance, these all play huge roles in determining how quickly and widely automation actually happens in practice.
So can be automated doesn't mean will be automated anytime soon.
Precisely. But even if only a fraction of that technical potential is realized, the impact could still be immense. Think again about autonomous vehicles. Their impact isn't just about replacing drivers, right?
No, it could ripple outwards. You mentioned changing how we use capital, like cars that sit parked most of the time now.
Exactly. It could revolutionize capital utilization. It could impact retail through automated delivery systems. It could dramatically improve safety, saving lives, and reducing healthcare costs. These are potentially enormous societal gains that just haven't been fully realized or measured yet.
And the sources seem to emphasize that if we want to actually see AI's full productivity potential realized sooner rather than later.
Then a critical and perhaps currently underrated area for research and investment is precisely the development of those complementary innovations we've been discussing.
The organizational changes, the new skills development, the new business models needed to leverage AI effectively.
That's where a lot of the bottleneck might be right now, building out the ecosystem around the core AI technology.
Okay, so as these automation capabilities grow, the conversation inevitably shifts, and often with some anxiety, towards the impact on the workforce, on jobs. The task-based framework is the standard way economists approach this, isn't it?
Yes, it's a very useful way to think about it. It helps break down complex jobs into the various discrete tasks they involve.
And within this framework, you have what's called the displacement effect.
Correct. That's the core direct impact where machines or AI systems take over and replace human labor in performing specific tasks. This naturally tends to reduce the demand for labor and potentially wages for those particular tasks or the skills associated with them.
But that's not the whole story, right? The framework also includes countervailing forces.
Exactly. There are other effects that push in the opposite direction. One is the productivity effect.
How does that work?
When automation lowers the cost of producing something, it can lead to lower prices or higher quality, which often increases the overall demand for that product or service. This increased demand can, in turn, increase the demand for labor in the tasks related to that product that haven't been automated.
So cheaper production leads to more demand, which needs some human labor, even if other parts are automated.
Potentially, yes. Other factors like capital accumulation spurred by the automation and the deepening of automation into further tasks also play complex roles.
However, the sources suggest these effects alone, the productivity effect, capital accumulation, are often not quite enough to fully offset the initial job displacement.
Or to prevent labor's overall share of the economic pie from potentially shrinking as automation progresses. They help, but might not be sufficient on their own.
So what has been the most powerful countervailing force historically, according to this framework?
The most significant force counteracting displacement, historically speaking, has been the creation of entirely new labor-intensive tasks. This is sometimes called the reinstatement effect.
Can you give historical examples of this reinstatement effect?
Think about the Industrial Revolution. As automation displaced artisans, entirely new categories of jobs emerged: engineers to design the machines, machinists to build and maintain them, managers to oversee the new factory systems, clerical workers, and so on.
Or later, as agriculture became heavily mechanized, displacing farm labor.
New jobs emerged in manufacturing and service sectors that absorbed much of that labor. So historically, technology didn't just destroy old tasks, it also created demand for new ones, often requiring different skills.
But you mentioned skills. Is that a potential friction point in this process?
Yes, it's a major one. There's often a significant mismatch between the skills required by the new tasks and technologies and the skills possessed by the workers displaced from the old tasks. This friction slows down the adjustment process and is seen as a significant contributor to rising income inequality.
And the sources also raise another interesting point, the possibility of excessive automation.
Right. This is the idea that firms might sometimes choose to automate tasks, even when it's not necessarily the most efficient or productivity maximizing choice from a societal perspective.
Why would they do that?
Perhaps for strategic reasons, like gaining market power, reducing their reliance on labor unions, or taking advantage of tax systems that might favor capital investment over labor hiring. These factors could lead to more automation than is strictly optimal for overall economic welfare.
This brings us squarely to the modern debate, the big question everyone asks. As AI gets better and better, especially at cognitive tasks, will it finally lead to long-term structural unemployment? Or will new jobs and demands emerge to absorb displaced workers, as they generally have in the past?
That's the crux of the debate. The more, let's say, pessimist view often centers on the idea of skill-biased technical change, or SBTC.
Explain that concept.
The argument is that just as earlier waves of automation primarily replaced physical, manual labor, AI is now increasingly capable of replacing cognitive labor, especially tasks that are routine or predictable, even if they require thinking.
So things like data entry, basic analysis, maybe even some forms of writing or coding.
Potentially, yes. And the SBTC argument suggests this could disproportionately increase demand for very highly skilled workers, those capable of complex abstract reasoning, creativity, or managing the AI systems, while simultaneously decreasing demand for lower and middle skilled workers whose routine cognitive tasks are being automated.
Which would tend to widen the gap between high earners and everyone else, exacerbating income inequality.
That's the concern expressed in that line of argument. The analogy sometimes used, perhaps starkly, is that of horses. Mechanization made their primary task pulling things obsolete, and demand for horses plummeted. Could certain categories of human labor face a similar fate if their core cognitive tasks are automated away?
Are there studies looking at the impact of modern automation, like robots?
Yes. The sources cite some important research looking specifically at the impact of industrial robots in U.S. commuting zones, mostly between 1990 and 2007.
What did that research find?
One prominent study by Acemoglu and Restrepo estimated a significant negative effect on local labor markets. They found that each additional robot per 1,000 workers reduced the employment-to-population ratio in that area by about 0.18 to 0.34 percentage points.
How many jobs does that translate to per robot?
Their estimate was that one additional robot led to a reduction in employment of about 6.5 to 7 workers in that commuting zone. That same study also estimated that one robot per 1,000 workers reduced average wages in the area by about 1.2% to 1.6%.
Those sound like pretty significant localized impacts from industrial automation even before the current AI wave.
They are non-trivial effects, yes, particularly in the manufacturing-heavy areas most exposed to that wave of robotics.
Okay, so that's the more cautious, perhaps pessimistic perspective. What about the optimist argument?
The optimist argument often starts by invoking the historical pattern, sometimes referred to as the Luddite fallacy.
Which is the observation that fears of mass technological unemployment have surfaced repeatedly throughout history, but they haven't generally materialized in the long run.
Exactly. Optimists might apply a concept similar to the Jevons paradox, which originally related to energy efficiency to labor.
How does that apply here?
The idea is that increased productivity through AI lowers the effective cost of producing certain goods or services. If the demand for that output is sufficiently elastic, meaning demand increases a lot when the price falls, then the lower cost could lead to such a surge in overall demand.
That the total demand for human labor involved in producing it, perhaps shifting towards complementary tasks, actually increases, even though the original task was automated.
That's the potential mechanism. The example of airline pilots often comes up here.
Right. You mentioned that earlier. Jet technology made individual pilots vastly more productive in terms of, say, passenger miles flown per hour.
But did that lead to fewer pilots? No. The lower cost and increased speed of air travel led to an explosion in demand for flying, which ultimately increased the total number of pilots needed globally.
Are there other examples?
Another compelling one discussed in the sources is bank tellers and ATMs. ATMs automated the routine task of dispensing cash, making tellers much more productive at that specific function.
So did teller employment collapse?
Quite the opposite. For several decades, actually, banks found that ATMs lowered their operating costs. They responded by opening more branches, making banking more accessible, and the role of the teller shifted
Away from just transactions
towards more complex, non-routine tasks that ATMs couldn't do, building customer relationships, explaining different financial products, sales, problem solving, skills that are complementary to the technology. The result, counterintuitively, was an increase in overall bank teller employment for a long time after ATMs were introduced.
That's a fascinating example of task shifting and complementarity. But the sources also add some crucial caveats to this optimistic view, don't they?
They absolutely do. It's important not to overgeneralize. These optimistic examples, like pilots or tellers, don't necessarily apply to every job or every sector.
Displacement can certainly happen if there aren't enough valuable complementary tasks for humans to shift into, or if the skills mismatch between old jobs and new tasks is too great for workers to bridge.
Precisely. The outcomes depend heavily on factors like how flexible the labor supply is, can workers retrain and move easily, and also how sensitive is the demand for the final output to changes in price or income. If demand doesn't increase much when prices fall, the productivity effect won't be strong enough.
And theoretically, some specific jobs could become almost entirely automated, leaving very little scope for human involvement.
Yes, that possibility exists within the framework. It's not guaranteed that complementary tasks will always emerge or be sufficient.
So, as we look ahead, AI is clearly demonstrating increasing capabilities in tasks we once thought were uniquely human. Even if, as the sources note, current AI is often more of an artificial likeness built on pattern recognition from data rather than a true imitation of human brain processes like some early AI research aimed for.
Thinking back to Deep Blue beating Kasparov versus trying to build a complete digital brain, for instance.
The capabilities are still advancing rapidly. Does this raise possibilities beyond just replacement, maybe towards more human-machine collaboration or even enhancement?
That potential for symbiosis definitely exists and is an active area of research and development. But navigating this transition effectively, however it ultimately unfolds, whether more displacement, more symbiosis, or a mix, will likely require some significant societal-level responses and precautions.
What kinds of responses or policies do the sources suggest might be necessary to navigate this era?
Several ideas come up in the discussion. One that gets a lot of attention is universal basic income, or UBI.
The idea of providing a regular, unconditional income floor to all citizens.
Yes. Proponents suggest it could potentially decouple basic survival from traditional employment, provide a crucial safety net for people whose jobs are displaced while they retrain, and perhaps offer more dignity and security in a rapidly changing job market.
Are there examples of this being tested?
The sources mention a trial in Finland, for instance. While it didn't show a significant overall increase in traditional employment among recipients compared to a control group, it did report positive effects on participants' perceived well-being, stress levels, and even some increase in small business formation.
Interesting. What other ideas are mentioned besides UBI?
There are related concepts like an AI dividend, perhaps funded by some form of tax on automation or on the profits generated by AI, with the proceeds redistributed to the population.
And education seems critical.
Absolutely. There is a clear consensus on the need for dramatically scaled up, effective reskilling and lifelong learning programs to help the workforce adapt and address that skills mismatch problem we discussed earlier.
What about the ownership or control of AI itself?
The concept of decentralized AI ownership is also floated. This could involve promoting open source AI models or exploring cooperative or collective ownership structures, potentially as a way to distribute the benefits and control of the technology more broadly across society.
And are regulators starting to grapple with these issues?
Yes, there are early discussions happening around regulation, reflecting a growing awareness of AI's profound societal implications. The European Parliament, for example, has issued reports considering civil law rules for robotics, raising important questions about legal liability, safety standards, and ethical considerations.
Sort of building conceptually on early philosophical ideas like Isaac Asimov's laws of robotics, but trying to make them concrete for legal and ethical frameworks.
Exactly. It's a starting point for thinking systematically about how we want these powerful technologies to behave and how we integrate them into our society responsibly. The sources make it clear that these transitions involve complex economic, societal, and ethical considerations. Proactive measures and careful ongoing considerations seem key to navigating this era successfully.
So, wrapping this up, we're left with this core tension, aren't we? On one hand, the incredible, undeniable potential of AI technology.
And on the other, the complex, often underwhelming, and sometimes puzzling reality of its measured impact on aggregate productivity and the labor market, at least so far.
And understanding this paradox really requires us to look beyond just the shiny new technology itself.
It involves grappling with fundamental questions about how we measure economic value, especially in a digital and intangible economy. It involves considering how the gains from technology are distributed or concentrated across society.
And perhaps most importantly, as the sources suggest, it requires appreciating the lengthy, complex, and often very costly process of developing and implementing all those necessary complements.
The changes in organization, the development of new skills, the investment in new forms of capital, all the things needed to allow AI's underlying promise to actually translate into widespread economic gains that show up clearly in our statistics.
And while those historical parallels with electricity and IT offer some comfort, some optimism regarding the potential for new tasks to eventually emerge and for future productivity growth to maybe accelerate again.
The sources make it very clear that this positive outcome isn't automatic or guaranteed. The potential for skill-biased technological change to exacerbate inequality and the reality of the displacement effect on workers whose tasks are automated mean the future of work and productivity is highly uncertain.
It seems it will require very careful consideration and potentially significant societal adjustments to navigate this transition equitably and effectively.
So, perhaps a final thought for you, the listener, to consider. Given that knowledge, as the sources imply, is most valuable when it's really understood and applied, and that adapting to change seems crucial, what role do you personally see for adaptability, for continuous skill development, and maybe even for rethinking our traditional definitions of work and value as we navigate this era of incredibly rapid technological change? What stands out most to you from our deep dive today?